This video I'll be discussing linear and angular speed. So the easiest way to unpack both of these concepts is just through an illustration. Suppose a runner runs on a circular path 100 feet in 5 seconds. What is her linear speed? What is her angular speed? So let's talk about linear speed first. And I forgot to write down, but linear speed, what we want is feet per second. Okay, so linear speed, feet per second. Anytime we're talking about something that is measured in linear speed, we always have a distance divided by time. So, and not just distance, we want to know how much distance has been traveled, or what is the change in distance. So I'll say distance traveled divided by time. And in this particular example, we want feet, the number of feet traveled divided by time. Well, it tells us right off the bat, 100 feet in 5 seconds. So we're going to say 100 feet over 5 seconds. So the linear speed, just divide 100 divided by 5, we have 20 feet per second. All right, so linear speed, I think most of us are pretty familiar with this. This is just the distance divided by unit time. How much distance have we traveled divided by unit time? Now let's talk about the angular speed. I forgot to write one thing down. On the circle, suppose the radius of this circular path, or the circle that the runner is following, has a radius of 40 feet. Okay, so visually what's happening is we have a runner. She's, let's say, running along this very poorly drawn circle. And the radius of the circle is 40. Okay, so she goes 100 feet in 5 seconds. So let's suppose she starts here, she ends up over here, and that's a distance of 100 feet. Okay, and it took her 5 seconds. So we saw that the distance that she travels in those 5 seconds, well, the 100 feet over the 5 seconds, so her linear speed is 20 feet per second. Now, when we're talking about angular speed, what we want to say is what angle has changed, or what angle has this runner passed through on the circle per unit time. So let's actually, let me redraw what's happening down here. So if the runner starts at this position and then runs 100 feet, they end up over here, there's some angle that on the circle that she has passed through. So angular speed is saying what is that angle she passed through divided by unit time. So we'd say change in angle divided by the unit time. So the question is, what is this angle that she has passed through? Well, if we think back to the arc length formula, S equals R times theta, well, we have the arc length here. The arc length is 100 feet. We have the radius, which was 40. So that'll tell us what that central angle is. So theta is going to equal 100 divided by 40, which is 2.5. And this is in radians. And it's in radians because in this formula up here, theta must be in radians. So 2.5 radians is the angle that she has passed through. So what we're going to say is 2.5 radians per unit time that has passed, which is 5 seconds. 2.5 divided by 5 is 0.5. So 0.5 radians per second. That is her angular speed. It's the change in angle per second. So she's gone half a radian per second. All right, second example. Find the angular speed in radians per second. That's C. for the tip of a 22-inch lawnmower blade that is rotating at 2,500 revolutions per minute. Okay, so the given value here is 2,500 revolutions per minute. So 2,500 revolutions per minute. And what we want to get to is radians per second. So first of all, we're given this rate in revolutions per minute, but we want this to be in our unit to be in seconds. So what I'm going to do is I'm going to convert from minutes to seconds here. So 60 seconds is equal to 1 minute, so that is going to cancel out the minutes. So now if I was to multiply this out, I would end up with revolutions per second as my units. So we're one step closer, but we need to convert revolutions into radians. So what does this even mean? So if we have a lawnmower blade that's 22 inches long, 1 revolution is when this blade rotates all the way around. So 1 revolution is equal to an entire rotation, an entire circular rotation. So in degrees, that would be 1 revolution is equal to 360 degrees. However, we want radians over here. So 1 revolution is equal to 2 pi radians. So 1 revolution like this. Okay, so the revolution can cancel. So we would end up here is our units, on the numerator we have radians, in the denominator we have seconds. So I just need to multiply through 2,500 times 2 pi. That's going to be 5,000 radians divided by 60. There's nothing to multiply there. So 5,000 pi divided by 60 radians per second. And if we multiply this out, 5,000 pi divided by 60, we end up with 261 points, let's call it 8 radians per second. Now, suppose we want to find out what the linear speed of the tip of this lawnmower blade. And let's say I want that in, let's say, feet per second. So again, I'm going to start with 2,500 revolutions per minute. I want to get to feet per second here. Okay, well, again, I need to convert from minutes to seconds. So 1 minute is equal to 60 seconds. So the minutes cancel. So I have minutes, revolutions divided by second. But I want feet. So how many feet have been traveled in 1 revolution? Well, if I take this, if I go back to my lawnmower drawing, 1 revolution, how far has that lawnmower blade traveled? Well, that distance, we call that the circumference. So the circumference is equal to 2 times pi times the radius. So the radius is 11, so 2 times pi times 11, so 22 pi here. And we were in inches, so this is going to be in inches. So 1 revolution is going to be equal to 22 pi inches is equal to 1 revolution. That'll get the revolutions to cancel. And then because my units at this point would be inches divided by seconds, and since I decided to say feet per second, I'm going to need to convert inches into feet. So there are 12 inches in 1 foot. Okay, so we could just multiply straight across. Those inches are going to cancel, and that'll get us our value. So if you multiply this out and then divide using the calculator, 55,000 divided by 720, so it comes out to about 76 feet per second. So that seems like a lot. that seems like that lawnmower blade is moving pretty fast. Now suppose we want to be able to convert between angular speed and linear speed. One way to do this is we would say W is equal to V divided by R, where W, this is a Greek letter. I'm not good at writing the Greek letter W, but it's omega. So W is the angular speed. V, or velocity, is the linear speed. And R is the radius. Okay, so often what we'll do, like that in that previous example where we wanted linear speed and angular speed, we could just find one of them and then use this formula to convert to find the other value. So let's actually look at that last example and convert, and we can check. And one thing I noticed on that last example is I forgot this pi right here in the calculation. So it should be 55,000 times pi divided by 720. And when we do that, we get 239.98. So 239.98 feet per second. So let's move those over to the next screen. Okay, so let's just plug in these values and the radius and see if this formula holds true. And if it does, that means these values would be equivalent to each other in a sense. So we need to figure out what the radius is. Now the radius, it said the lawnmower blade was 22 inches long, so the radius is half of that, so 11 inches. Now we need to be careful here because this is in feet. So 11 inches, to convert that to feet, we just do 11 divided by 12. So that's a decimal. I don't know what that is. Let me check on the calculator. It's about 0.9166, or we can just use 11 divided by 12. So plugging this in, 261.8 is equal to 239.98 divided by 11 over 12. And does that equal? And if you multiply, or if you divide out on the right-hand side, you do get 261.8. 261.8. They're not going to be this clean because we've rounded a little bit. We rounded these values along the way, but it does come out. So the moral of the story here is that if we would have just found the angular speed first, we would have just found this. We could have plugged it in, the angular speed here, and the radius, and solved for the linear speed. Alright, the last example says a model plane is attached to a swivel so that it flies in a circular path at the end of a 12-foot wire at a rate of 15 revolutions per minute. Find the angular speed and the linear speed of the plane. It's probably this swivel is hanging from the ceiling. We have the plane flying around in a circular path like this. Imagine what I'm drawing here is an airplane. And it's kind of traveling in this direction, so it's flying around in a circle. Alright, so how are we going to do this? So the path, 12-foot wire at a rate of 15 revolutions per minute, find the angular speed. So I think actually how this is, this diagram isn't quite representative of what's happening here. So the swivel is kind of more perpendicular here. So we have 12 for the radius. All right, so thinking about what we had before with this formula, angular speed is equal to linear speed divided by the radius. We had the radius, it's 12 feet. So we can either find the linear speed or the angular speed and then use that formula to convert. So what do we want to do here? I'll find the linear speed first, I guess. It doesn't really matter. So we have the current speed is 15 revolutions per minute. And it doesn't really say what unit to use at the end. So because the radius is in feet already, I'm just going to say feet per, we can just use minutes again. So we already have minutes, so 15 revolutions per minute. So one revolution, what distance is getting traveled in one revolution? Well, one revolution, again, we can call that the circumference. So circumference is equal to 2 pi r. The radius is 12. 12 times 2 is 24. So 24 pi feet would be the circumference here. So one revolution travels through 24 pi feet. The revolutions cancel. We're left with feet divided by minutes. That's what we want. 24 times 15, 243, 60. So we end up with 360 feet per minute. Sorry, don't forget the pi. 360 pi feet per minute. So if I type that into the calculator, we end up with about 1130.97 feet per minute. All right, and then if we want to convert that into an angular speed, well, we're going to say 1130.97 divided by the radius. The radius was 12. Now this over here was in feet per minute. The radius is also in feet, so that's good. So our units are lining up. So we're just going to divide that by 12. We end up with 94 point, let's call it 25 radians per minute.